Here we go, video notes 8.2. It's Mrs. Harbin signing in for you. We're going to do these 4 things, so get ready. All right, lots of objectives for this PowerPoint, so let's do it. All right, please read Chapter 9, Sections 9.4 and 9.5. Read through example 9.7, and it's on page 53. Please copy or summarize the steps for solving stoic problems involving limiting reactions from page 255. You will be glad you did. Okay, so remember the tricycles? How many tricycles? All right, so here's the formula for tricycles. What if I have 6 wheels? Then I will be able to make 2 tricycles, right? But what will I need for sure? 2 frames. Well, what's the deal with that? What if I only have 1 frame available? So if I have 6 wheels and 1 frame, guess what, kids? I'm only getting 1 tricycle. So what does that mean? That means 3 of those wheels get used up, and I'll have 3 wheels left over, okay, excess. So here's what we're showing here. That one of the reactants in a chemical reaction, the amount that we have is going to limit how much product we get. If I had 6 wheels but only 1 frame, guess what? I'm only getting 1 trike. So that's the limiting reactant. And then I'd have 3 wheels left over, 3 wheels excess. So how can we do this stoichiometrically? All right, we need some definitions. A limiting reactant is a reactant that controls the amount of product. It's the reactant that gets used up. Okay, excess reactant is the one left over when the reaction's done. So once you know the limiting reactant, you use it for the calculations of the product because it's the one that determines the amount of product. Also, how do you know to do a limiting reactant problem? Well, you're given 2 amounts of reactants. So let's see it. All right, look, it's mercury and oxygen making mercury oxide. If we have 20 grams of mercury and we have 5 grams of oxygen, oh look, reactant, reactant, we're given 2 amounts of reactant. So I know I need a limiting reactant problem. So the easiest way to compare, or there's several ways to do it, lots of ways, but one easy way to do it is to compare how much reactants we have, how much of the reactants we have. So I'm changing my reactants into moles, and I find out that I have 0.0997 moles of mercury to use in this reaction. And I have, because I can only compare things in moles, 32.00 grams of O2 for every 1 mole of O2. All right, so this is old mole stuff. I get 0.156 moles of O2. So what does that mean? That means I have 0.997 of that, 0.997, 0.156 of that. But it's hard to decide because these aren't whole numbers. So I'm going to say, well, if all of my mercury gets used up, 0.097997 moles of mercury gets used in this reaction, I'm going to need to have, because there's 2 moles of mercury, mole ratio, for every 1 mole of oxygen, mole ratio, coefficients, I find out that I would need 0.0499 moles of oxygen. What does this mean? Okay, so what it means is that I have 0.156 moles of oxygen available, right? How do I know that? It says right here, all right. But I only will use 0.0499 moles of oxygen needed or required to react with all of the mercury. So what does that mean? All right, so it's saying if all my mercury gets used, I only need that much oxygen. But guess what I have? I have this much oxygen. So what this means is the limiting reactant is mercury. The excess reactant is oxygen. Okay, so that's how you decide what the limiting reactant is and what the excess reactant is. All right, so changing both the moles, compare, change one reactant into the other, and then see how much you have available versus how much is required. Okay, the one, if there's more available than required, that's excess. If there's less available than required, that's limiting. Okay, so now that we know, so let's go back to this. Now that we know that mercury is the limiting reactant, I can figure out how much mercury oxide should form in this reaction. Okay, how do you do that? Well, you take your limiting reactant, which is 0.0997 moles of mercury, and you change it into moles of mercury oxide. So I'm going to move this over a little bit because guess what? I ran out of room. So 0.0997 moles of mercury are going to be used up, and it's all going to be used up if everything works perfectly. And 2 moles of mercury will form 2 moles of mercury oxide. But guess what? I want to know the maximum amount in grams of mercury oxide. So I'm not going to stop at moles of mercury oxide. I'm going to say, well, for every 1 mole of mercury oxide, I'm going to go get the grams from the periodic table, and it's 216.59 grams. So what does this mean? This means that I should get 21.6 grams of mercury oxide in that chemical reaction. Okay, step 1, figure out which of these 2 reactants is limiting. How do I know to do a limiting problem? Reactant, reactant. Step 2, after you figure out which one's limiting, use the limiting reactant to predict the maximum product you can get. Okay, what does it mean to calculate excess? Excess is the leftover, so it's waste. Why do we want to know about the excess reactant? Well, making chemicals cost money, moolah. So if we know how much waste material we're going to have, then we can make sure we don't have too much waste material. And we can make our cheaper reactant, if one reactant costs more than the other, we can make our cheaper reactant be the one we have excess of, and then the reaction will be cheaper. So if you want to calculate the amount of excess reactant, you have to start with the limiting reactant. After you start with the limiting reactant, convert it to the excess reactant. And that tells you what you need to complete the reaction. Then you subtract how much you needed from how much you had, and you have the leftover. Well, it's practice. All right, so let's say we had 90 grams of iron chloride reacting with 52 grams of H2S. How do I know it's a limiting reactant problem? Well, 2 reactants, reactant, reactant. Find the mass of HCl produced, find the mass of excess reactant. Okay, so step 1, change grams of each reactant into moles. Boom. Okay, and so there is 160. Where am I getting 162.2 grams? Well, I checked the periodic table, found 3 chlorines, added together, found an iron, added it, and here we go. I find out that this reaction, if I'm using 90 grams, I'm going to have 0.55 moles, 555 moles of FeCl3. Okay, and if I have 52.0 grams of H2S, I'm going to have periodic table 34.09 grams of H2S for 1 mole of H2S. I find out I have 1.53 moles of H2S. Okay, so I have to change one reactant into the other to see how much I'm going to use up. So I will use the 0.555 moles of iron 3 chloride, and I'll use the mole ratio to compare the moles of iron 3 chloride to the moles of H2S. One reactant to another. Alright, so there's 2 in front of iron 2 chloride, 3 in front of H2S. So then I calculate it out, and I find out that 0.555 times 3 divided by 2 is 0.833 moles of H2S. What does this mean, you're saying? Alright, so what it means is this is what I have available, and that's what I have available. If all of this gets used up, I need that much. So let's write it out. I have 1.53 moles of H2S available. How do I know that? I changed the given grams into moles. I know that's greater than the 0.833 moles of H2S required. So I find out H2S is the limiting reactant. Okay? Alright, once we know, I'm sorry, I said H2S is limiting. I lied like a dog. Alright, I don't know if dogs lie, but anyway. This is how much I have available, this is how much required, so you can see there's more available than is required, so H2S is excess. Hey, don't go, I know it's the bell, but it's turning into 8th period on Friday right now. So that means FeCl3 is limiting. Okay, what do I do after that? Well, check, found the limiting reactant. FeCl3 is limiting. The mass of HCl produced. Okay, and then what mass of excess reactant? Okay, so how do I figure out how much HCl will be produced? Well, I have to use the limiting reactant. So you find the limiting reactant, and then you use the limiting reactant. So let's use the limiting reactant. The limiting reactant is FeCl3. 555 moles of FeCl3. And I know that for every 2 moles of FeCl3 coefficient, I will make 6 moles HCl coefficient, but I want mass of HCl, so I say 1 mole of HCl has a mass of 36.46 grams HCl periodic table, and I find out that there will be 60.7 grams of HCl produced if all of the iron chloride gets used up. Okay, so that's question 2, mass of HCl produced. Hey, what's the third? What mass of excess reactant remains after the reaction? Okay, well, we know H2S is excess. We know 0.833 moles of H2S gets used. So I can say, well, if I have 1.53 moles of H2S available, I'm going to use up 0.833 moles of H2S. That's what was the required amount. What is that? What do I have left over if I subtract those two? 0.697 moles of H2S left over. Excess. Leftover excess. So it says mass, so I changed 0.697 moles of H2S times, I know every 1 mole periodic table H2S has 34.09 grams of H2S. So I find out that there will be 23.8 grams of H2S left over in that reaction. Excess. All right. I know it's complicated, but if you do one example, then when I do another one, it'll maybe start being clear. Okay. Here's another balance equation. Woohoo! You gotta have them. If I don't give you a balance equation, you have to write and balance it yourself. Okay. So we have iron 2 oxide, and that's reactant. Look, reactant. Aluminum reactant. 2 reactants. So this is going to be a limiting reactant problem. Okay. So first we have to find the limiting reactant. Then we have to find how much iron we can make. And then we can find out how much excess reactant is left over. Okay. So I wonder if I did this one in my notes already and I didn't. So what I want you to do is save this one. But let's do this. 10.35 grams of FeO times grams of FeO, 55.85 plus 16. 55.85 plus 16 equals 71.85 grams of FeO for 1 mole of FeO equals, and then 4 grams of aluminum. The other reactant, 26.98 grams of aluminum. 1 mole of aluminum equals, and so we're going to get moles here. All right. Step 1, grams to moles. Got it. Then pick one of those two, all right, and change it into the other one. So let's just say, so pick one of those two and change it into the other one. Then, whichever one of those is limiting, use the limiting reactant to turn it into product. All right. And then subtract available excess reagent minus available excess minus used up required gives you moles of excess. All right. And then once you have moles of excess, you can change it into grams. And then moles excess, change into grams. All right. So that's how you do it. I will work through this one in class. So leave space in your notes for that. All right. One other thing that two other things we're going to learn here. You know, combustion reactions always give off carbon dioxide and water because they're burning stuff. That's not the only thing they give off. They also give off light and heat. So we're going to start treating heat as a product or as a reactant. In combustion reactions, it's going to be a product. In other reactions, it could be a reaction. reactant. So heat can be given a coefficient. Look at that heat. All right, so let's find it in the next reaction. Are you ready? So here's a reaction. Find the heat 1, 2, 3, 4 here. What side of the arrow is it on? Product side. So does that mean the heat is given off in this chemical reaction? All right. Thanks, Glenn Fry, for your support. So we can use heat in stoic. In this case, heat is a product. So how much heat is released if 75 grams of aluminum react? All right, only given one reactant. All right, and hey, starting 8th period today, Friday. So 26.98 grams of aluminum for 1 mole of aluminum. Now, I'm going to use this balance equation, and these are my coefficients. All right. This is my heat coefficient. Instead of being moles, it's kilojoules because it's heat. So if I want to know how much heat is given off, I say, well, for every 2 moles of aluminum, why? Because that's a coefficient, 2, 2, there's 55 kilojoules of heat produced. So then I would do the math, and I would find out 75 divided by that times that divided by that, 76.4 kilojoules of heat is released if I react 75 grams of aluminum. Okay, so heat can be used as a coefficient, and actually it's one step shorter because you stop with kilojoules. All right, what if you're given kilojoules? 125.5 kilojoules. All right, well, looking at this balance equation, look, there's the heat. All right, so I use my balance equation, the 55 kilojoules from the balance equation, and then what am I trying to find? Find grams of iron. So I want to go, my heat is like a coefficient, so it's kind of like moles. But I find out that there's 3 moles of Fe for every 55 kilojoules. But I want grams, so I'm going to say moles are number 1. Periodic table is going to get the grams. Right. So I find out 382.3 grams of iron. All right, so heat can be used as a coefficient. If heat's on this side, this number can be compared to any moles of that. It can only be heat in moles. Moles, heat, coefficient of heat, coefficient of aluminum. Moles, heat, coefficient of moles, coefficient of heat. Okay. How much heat is required to use 58.6 grams of potassium chlorate? All right, so we'll do this one now, and we'll do the other one in class. So we have 58.6 grams of KClO3. We want to find out heat. Oh, look, here's a heat coefficient, mole coefficient, mole coefficient, mole coefficient. This is grams. So 122.55 grams of KClO3 for every 1 mole of KClO3. Phew, luckily spent a whole chapter on moles. Whew. But now the new stoic stuff, there's a 2 for moles, 2 moles KClO3. And what's the heat coefficient? 195.3 kilojoules of heat. All right. So look, grams cancel grams, periodic table, thank you. Moles cancel moles, see ya. We're left with kilojoules. And we find out that there's 46.7 kilojoules of heat. Now look at the heat is on the reactant side of the arrow, so that's added in, so that's absorbed. All right. If it's on the product side, it's released. If it's on the reactant side, it's added in. All right. I want you to try it. I'm going to do it in class. We have this many liters of O2. We want to know how much heat. Find kilojoules. All right. So try that one. All right. So there's other ways to describe these reactions with heat in them. Okay. This one right here, the heat's on the reactant side, so it gets added into the reaction, just like all the reactants get added in. If heat is added in, it means it's endothermic. Endo, added in, added into the reaction. Exothermic means heat's leaving. Bye-bye heat. Bye-bye heat. Let's do it like that. Bye-bye heat, leaving. You feel it. The heat is on. You feel it exothermic. Okay, so endo means into. Heat goes into the reactant side of the reaction. It's going to be on the left side of the arrow. Heat, endo on the left of the arrow. Exo, it's going to be on the right. Endo is going to feel cold because heat's being absorbed by the reaction, so it absorbs energy. Well, what's the difference? Exo is the opposite of all of that. So here's a way to remember it. Plendo. All right. You see the word endo in there, okay? That means the heat is positive, it means being added in. It's on the left side of the arrow in a chemical reaction. Plendo, positive left endothermic, means it absorbs heat. So let's look back. Hey, there's heat in this reaction. Where is it? It's on the product side, so this is an exothermic reaction. All right. Oh, look, another reaction. Find the heat, found it. Where's the heat? It's on the reactant side. That means being added into the reaction, so this is endothermic reaction. Okay. Now, another way to describe heat is called the delta H. Put this in your notes. Delta H can have a positive sign if it's added in, so that's endothermic. Delta H could have a negative sign. That means it's exiting, so it's exothermic. All right. We'll get into it in class, but here's what I want you to know. Bond breaking requires energy. If you had a broken bone, what happens? Well, energy is added in to break your bone, right? Just like energy is breaking bones, ouch. Added energy to break bones. Added energy. So guess what? Breaking bonds is kind of like breaking bones. Added in, endothermic. Endothermic. Breaking bonds is endothermic. All right, but making bonds, when that bone goes back together, it's a relief, releases energy. So bond formation releases energy, so it's exothermic. Otherwise, bonds wouldn't form. There'd be no driving force. Okay. Last but not least, percent yield is part over total. Percent yield is part over total. So, what is the part? Part is what you get in an experiment in the lab. So if I go in the lab and make some sodium chloride, that's the part. That's what I make in the lab actually in the experiment. Total is what Stoic says you should have made. This is sometimes called theoretical or expected. The total comes from the limiting reactant. So percent yield equals actual yield, what you get in the lab, experiment, what you get in the experiment, divided by, that means the same thing, divided by theoretical yield. Theoretical yield. That's what you expected to get from Stoic. From Stoic. All right, but again, it's part over total. Parts from the lab, total is what you think you should get from Stoic. Okay, how is that different than percent error? Percent error is actual minus theoretical, and we'll absolute value that, over theoretical, times 100. Okay, so percent yield is what you get. Percent error is how far off from what you get. Let's practice. Calculate the percentage yield if 550 grams of C7H8 reactant makes 305 grams of p-nitrotoluene product. Okay, reactant product. So we want percent yield, so we need a part and we need a total. All right, so what's the part? The part is what comes in the lab. It comes from the lab. So, and it has to be product. 305.1 grams of p-nitro. Okay, toluene. Ooh, when you take organic, you can learn about that. That's C7H7NO2. But we need a total. Where do we get a total? A total comes from Stoic using the limiting reactant. This only has one reactant, so we must assume that there's enough nitric acid to go around. So we take our reactant and we change it into product. 92.15 grams of C7H8 is 1 mole of C7H8. Always go through moles. For every 1 mole of C7H8, we are going to make 1 mole of C7H7NO2. Woohoo! That's a good mole ratio. But our product is given in grams, so we need our C7H7NO2 prediction to be in grams. And so it's a 137.15 grams. Where did I get that? Periodic table. Where did I get that periodic table? All right, when I calculate that, I find out that I should get 818.6 grams of C7H7NO2. What does that mean? That means if all of this reacts, I'm predicting using stoic. I'm expecting theoretically to get 818.6 grams of this. How did I do that? Change the reactant into product and predict it. Did I do a reaction? No, I'm just predicting. So this is our expected or predicted or theoretical, any way you want to call it. It's what stoichiometry tells me, times 100. That's going to be a 37.27% yield. So what does that mean? That means I started the reaction with this many grams of C7H8. I predicted to get this many grams using stoic. Theoretical yield comes from stoic. Actual, what comes in the lab, I went into the lab and I made this, and this is theoretical, comes from stoic. All right, comes from stoic. Theoretical comes from stoic. So where do you get theoretical? It's from stoic. What do you use? The limiting reactant. Okay, and that is a percent yield. Okay, another one. 1.85 grams of aluminum, 2.12 grams of copper form. So this is product, this is reactant. Right. So this is not a limiting reactant problem, or I'd have 2 amounts of reactants. So fortunately I was, hey, wait a second. I have to balance this equation, don't I? You betcha, Mrs. Harbin. So I'll put a 3 there, 2 there, and a 3 there. 2 aluminum, so yeah. Okay, so you might have to write an equation, you might have to balance it. So 1.85 grams of aluminum going into the reaction. Here's me predicting what should come out. 26.98 grams of aluminum for 1 mole. Periodic table. Now that I'm in moles, I can say moles to moles. Why am I going to copper? Because the product they tell me about is copper. So I know that for every 2 moles of aluminum, I should get 3 moles of copper coming out of that reaction. But my percent yield is almost always in grams. So 1 mole of copper has a mass of 63.55 grams. Where did I get that? Periodic table. Okay, so this is me doing stoic to predict the theoretical yield. Okay, that's how many grams of copper should come out of the reaction if that goes in. This goes in, this should come out. That's theoretical. I didn't do a lab to do that. I just predicted. So percent yield, I put that on the bottom. Okay, and then this is actual product that I made in the lab. 2.12 grams of copper actually made in the lab gives me a 32.4% yield. Okay, actual, theoretical. Where'd I get the theoretical? From stoic. Where'd I get the actual? I made it in the lab, you betcha. All right, to review, it was a long time ago, about 8 minutes ago. What is the limiting reactant? It controls the amount of products, and it doesn't need to be in moles, so it might be given in grams. You got to figure it out. The excess reactant is the leftover, so we want it to be cheap because that's what chemists want. Limiting reactant calculates amount of product to get theoretical expected yield, and it is used to tell us how much excess is needed, so we can figure out how much excess is left over. Always go through moles, moles, moles. Hey, what about the heat? Okay. Well, don't forget that percent yield is part over total. The part is the actual. The total is stoic times 100. That's for percent yield. Percent yield. How much do we get? Total is from stoic. Total is from stoic. Okay, using the limiting reactant. The other thing I want you to remember from this video notes is plendo. Endothermic reactions have a positive heat going in on the left side of a reaction. All right, treat heat like a reactant or product, and always go through moles. It was long, but it was fun, and the heat is on for you. If you go to this, you'll get some steps to help you figure out the limiting reactant. Did I just sing? Anyway, peace out. I know it was long, but hopefully you learned all this. The heat is on.